just like last time, X will be the Higgs branch. Some gauge theory, 3D n equals 4. So there is some complex moment map, and there's this quotient of the stable locus, and it is you can think of it as an open. It's an open subset in some quotient stack. And recall that, okay, a lot of people were talking about quasi-maps during this week, and that there's a stable quasi-map from some curve C to our X. Well, there's this notation like this. So it's just a map from C to this quotient stack such that it, which lands in X. So this, in other words, it gets into the stable locus for all but finitely many points of C. Okay, so and those finitely many points are singularities. And physically, I think of them as the limit of vortices, where you sort of look at it as the IR limit, where the size of the core of the vortex goes to 0. Now, let C be just the okay, and before an interesting class of axes are Quill varieties. So for Nakajima Quill varieties, this definition makes sense more generally, but in particular, we think of it as sections of homomorphic sections of the bundle. Let's call it M plus M star, which is twisted by this additional H bar, which distinguishes the cotangent direction, where M is like in the Nakajima Quill varieties, is there are certain humps between bundles I, V, J, curly P, with some multiplicity. They might appear with some multiplicity Qij, and also there are framing spaces W. So here these are just the associated adjoint bundles for the corresponding principal bundle. And the gauge group in this case is the product of UNs, right? So as you vary the data of these bundles, VI and it's also the data of the quasi-maps F. You get the modular space of quasi-maps into X, which are just quasi-maps up to certain isomorphisms. Now let me focus on the case when the curve is just P1, and then I'll consider quasi-maps that are non-singular at infinity. So, in other words, the infinity lands into a stable locus in the target. And then this is an open, again, subset in the full modular space of quasi-maps. And one can consider the evaluation at infinity, which is a map to X. And then there's a notion of vertex function, but it has many other names. And this, by the way, all is explained and introduced in Okunnikov's lecture notes on in K-theoretic enumerative, so K-theoretic counts of K-theoretic enumerative geometry. So you take the push forwards with respect to this map. Over certain, well, some virtual structure sheaf with also a weight introduced. There's a weight that measures the degree of the quasi-map. So it's a structure sheaf on the modular space, and as you take push forward, and you get some element of the K theory of X. Well, with an additional parameter for rotations of P1. That's localized, and then there's also this variable Z that measures the degree of quasi-maps. So I'm going to call it just V, V of X and Z, where X's are equivariant parameters for this torus T. Remember that the torus T acts on X. So T was this A, which preserves the symplectic form plus additional C star, which scales the symplectic form. So it's an interesting object. It counts these quasi-maps and has physical meaning. But before that, let me mention the following property. So again, X is Higgs branch, and then X check will be the Coulomb branch of the same theory. Now, in 3D n equals 4. Now, thanks to work of Peter and Justin and Davide and who else? Well, two more, I think Bullimore and we know now that the mathematical notion of symplectic duality, in physical terms, it's some kind of correspondence between the Higgs and Coulomb branches of the same theory. So suppose we have these two symplectic dual spaces, and we can consider the vertex function of x, and whatever it means, the vertex function of the dual space. Now, if at least if the dual space admits description as a hyperkähler quotient, then this applies, and it's clear what I mean by this object. If it doesn't, there still has to be some way to define it. Because physically, it's clear that, as you'll see, that this thing makes sense, both Higgs and Coulomb branches. Well, one can introduce a slightly different normalization of these objects. It's usually denoted V tilde, and here I'm going to follow Agamagi-Chokunkov. Slightly different normalization. Well, there's a prefactor which, in physical terms, it captures the Chern-Simons, the effective Chern-Simons terms in your theory at low energies. So I'm not going to explain what it is, but there is a certain polynomial expression here in logs of these variables. Then there's a product. Recall that in the definition of, in the discussion of stable envelopes, there was a choice of polarization of X. So here I will consider weights in the direction of this polarization with respect to the T towards T action, and then here's it. There's a certain expression where this notation goes under various names, Pockhammer symbol, quantum dilogarithm, and it's just a product. So one has this slightly rescaled vertex function, and there's a Q is the equivariant variable for rotations of P1, and P is a certain polynomial which I didn't want to explain. But roughly, it's like you get here expressions like log x, log z divided by log q, like expressions of this type in the exponential. And then there's a similar thing for the dual one. And there's a statement that these two vertex functions are related in an interesting way. Namely, well, first of all, here, since it's an element of this theory, you can expand it into the basis of fixed points. And I will write the corresponding function with an index p below, which denotes the fixed point. So I can expand the class on the fixed point basis. So, so this function, now it's just a function. It's related to the other one, the dual one, in the following way. So here's a matrix, and I sum over the fixed points. Well, just this T fixed points, assuming that they are isolated. This, and it also depends on X, Z, H bar, X, Z. But so there's this sum, and then in the result, I actually have to swap X and Z. Recall X are equivariant parameters, Z are Kähler parameters, and it's a common feature in this kind of oh, sorry. Yes, it's correct. I have to swap them. So if I could think about this object as a vertex function for the Higgs branch of the mirror dual theory. So this is Higgs branch of the original theory. This is the mirror dual one, and then under the 3D mirror symmetry, the equivariant and Kähler parameters, they are swapped. So that's why I would do this. But here, what's interesting is that it's not enough. One also has to act with this matrix. So call this the pole subtraction matrix. For the reasons that I'm not going to explain, but it's related to the fact that this function satisfies certain difference equations. And V and V dual give you different types of solutions of that equation. But it turns out that it's this matrix, it's proportional to the elliptic stable envelope with some proportionality factors, which I'm not going to explain. They are not, at least from this large scale point of view, they're not very important. The point is that there's this matrix which is invertible. It's upper triangular matrix. And it sort of mixes these different vacua. And well, just like stable envelopes depend on the choice of chamber, it also depends on the choice of chamber in which, well, as I explained last time, it depends on in which chamber the real masses to take their value. So anyways, can we understand this relation little better from the physical point of view, because of course Ramanujan OpenCode provides mathematical proofs. At least in a number of examples. Now the question is, why does it happen from the physics point of view? So, to proceed in that direction, let me introduce the half index. It is in general defined for a 3D n equals 2 theory. And in our case, we look at n equals 4. Broken to n equals 2 is like, this is called softly broken. So n equals 2 by this parameter h bar. Basically, this is because the torus C star, the h bar rotates the symplectic form. Well, it should have, okay, it's the p prime. Yeah, so V is and just it's V. You can think of it as a vector with components VP. I mean, it's an element of K theory, which I expand in the fixed point basis. So what is this half index? Well, you consider your 3D n equals 2 theory on the hemisphere, HS2 cross sphere, cross a circle, possibly with sometimes denoted like this, which means that as you go around the circle, you rotate your hemisphere and you compute the partition function of your three-dimensional theory on this space, which is going to be a number, or rather a function of various flat connections that you turn on along S1. In general, it preserves. So I should say that once you have quantum field theory, you can put it on different backgrounds, so on different manifolds, and most of the talks this week they were dealing with topologically twisted theories, which is just a particular type of background, but the full quantum field theory needs other types of backgrounds, and in particular here, there's no topological twist going on. Rather, so this background preserves two supercharges in general for 3D n equals 2 theory. So call them Q1, Q2. And well, I can consider their sum, which I'm going to call just Q, and this Q squares to if I denote the angle, parameterize this circle by an angle alpha, and denote this angle phi on the hemisphere, then it's going to be just a certain rotation. Let me write it like this: rotation along alpha, and the rotation along the phi direction, plus some other stuff. And physically this thing, it counts BPS operators. Perhaps I could call this not Q1 and Q2, but Q plus and Q plus bar. Counts boundary operators in your operators in 3D theory and 3D QFT. So operators that can be inserted along some boundary condition. And here, by the way, I impose some boundary condition along the boundary. That are in Q bar for homology. Of course, these operators, they form some boundary vertex algebra, and you can interpret this half index as its character. And these are this, in general, some logarithmic vertex algebra, similar to what was mentioned in Tudor's talk. But that was in the context of topologically twisted theories. Now, why am I talking about this half index? Well, because it's actually related to this object. Basically, it is equal to it for the right choice of boundary conditions. This background this supersymmetric background on a hemisphere across S1 that computes the half index admits a exact deformation where you extend the hemisphere into a long cigar and you keep the circle. Well, the words Q exact deformation means that basically the partition function, so the half index doesn't change as you perform this deformation. But once you perform this deformation, and so to be more explicit, I am going to write the metric. So here let me introduce spherical coordinates, because that's here this angle is theta, and I said that this one, the one that corresponds to rotation, the isometry of the hemisphere is phi, and this one is alpha. So here the metric on this space is determined by a certain function f of theta. So beta here is just the length, the circumference of the circle. Epsilon is a parameter that determines how much you twist the cigar as you go around the circle. So as you go around the circle, you rotate, it rotates. L is just the radius. This radius is L, right? And f of theta is the function that determines the shape of the cigar. You can take an arbitrary, put an arbitrary function here. So if it's just L, then you get back the round hemisphere, but you can extend it. And then on this background, one can perform the supersymmetric localization and get certain BPS equations. Similar to how, for example, some of the speakers earlier this week wrote generalized vortex equations that come from supersymmetric localization on the logically twisted background. Here, the technical term for the kind of localization that I want to perform is the Higgs branch localization, which is the one that gives you vortices normally. Let me actually write explicitly the equations that one gets. But they are specific to this type of backgrounds, so they are not extremely nice looking, but so sigma is the real scalar in the vector multiplet. There's F here is the gauge field strength, and then there's this equation that the F the moment map for the matter fields of your theory equals, and here there are two terms. One is like this, and one term with a gauge field strength. And there's one block of equations, and then there are some other equations for the matter. In particular, there's one so here phi is the complex scalar in the chiral multiplets, and m are real masses. Okay, I guess, and there are some other equations, but now what I want to focus on are this equation and this equation. If you look, so we have make this cigar very, very, very long, right? And then we can focus on this region or on this region. When I focus on the region close to the tip of the cigar, so here in this region, the theory approximately becomes a-twisted. So this is the 3D n equals 2 a twist. It's still not the same a twist that appeared in other talks, which is the fully topological n equals 4 twist. This one is only partly topological. But in this region, these two equations, they actually become the vortex equations, which are the BPS equations in the 3D n equals 2 a twisted theory. So they become well, the way basically the first term here, it's suppressed in this region, and one gets the usual vortex equations. It's just a star, two-dimensional star, F, and anti-holomorphic. And this one becomes just the second equation becomes just the anti-holomorphic with respect to this gauge field derivative. Whereas if I focus on the other region, this one, let me just draw it here because I want these two things to be close to each other. In this region, this effectively looks flat, and I get the gradient flow equations, which play a role in the construction of stable envelopes. So here I get gradient flow equation, namely, if I denote this direction now as y, which is slightly rescaled theta, actually. Then equation here become like this. So they're actually gradient flow equations for the Morse function where sigma is contracted with the real moment map for the gauge symmetry, and mass is contracted with the real moment map for the flavor symmetry. So the point here is that one gets this system of equations on such space which interpolate between the vortex equations on the one end and gradient flow equations on the other end. As I already said previously, I guess I'll just repeat it, that this thing is basically this V tilde, the rescaled vertex function. Now, an interesting property of this background is that I can start turning on various profiles for masses and for the phi parameters, so the stability parameters. It is possible to turn on masses. Roughly, you can imagine that if this is mass and this is the theta direction, and here is our cigar, you can turn on some mass profile along the cigar. At the same time, well, it requires also turning on some magnetic field for the flavor symmetry. But here, nothing depends at the level of Q cohomology. So at the level of supersymmetric observables, nothing depends on the shape of this m of theta, of this function m of theta. Only its value at the boundary, which is pi over 2, only this value matters. So I can use this, and actually then I can do the same thing for the Fi parameters. Same for Fi or mathematic stability parameters. I denote them by letter zeta. So I can use this property to do the following trick. So I consider this partition function on the cigar. Well, it's always times S1, but for simplicity, I will suppress S1. I'll just draw the cigar. And let's say that the mass is 0 here, but the Phi parameter is non-zero and it's very large. So it means, in this regime, means that the theory is in the Higgs phase. So at low energies, it looks like a sigma model into the Higgs branch, roughly. But then I can use this property that I can deform the profile of masses and consider the following thing. I have to keep the masses and Phi parameters unchanged along the boundary. So here, near the boundary, I still keep them masses 0 and Phi parameters large. But then I can deform them. So there's some transition zone here where they get deformed, and here I have instead masses very large, and the Phi parameters are 0. Well, what is this region? Well, it's basically the Janus interface that was introduced last time, but both for mass and for the Phi parameter. But it turns out that sort of in this Lagrangian description of quantum field theory, the mass one is more interesting. The Phi interface is kind of trivial to describe. And well, that is also related to the fact that on the Higgs branch, only the mass Janus interface triggers gradient flows, whereas this one doesn't. On the Coulomb branch, it's the opposite. The Phi parameters play the role of masses there and trigger gradient flows on the Coulomb branch. Anyhow, now this thing, I can sort of cut it and express it in the following way. There's going to be a sum over the fixed points. Let me call them alpha. So there are these fixed points, so vacua. Here I have this piece of the cigar with some boundary condition. Let me call it d alpha. And then cylinder here and alpha. And I also impose some boundary condition dp here, such that this thing is equal to vp tilde. And there's this interface such that mass is large here, 0 here, and the phi parameter is the other way around. Now, this quantity was the cigar partition function calculated in the Higgs phase. So here we have Higgs phase. This quantity here, where we sort of exchange the role of masses and the phi parameters, it is in the Coulomb phase. Which means that at low energies, you are studying basically maps into the Coulomb branch. And this one is proportional to the stable envelope. Because as I explained last time, this Janus interface is what realizes the stable envelope. Now, this partition function in the Coulomb phase is actually what V dual is. This is just the vortex function for the Coulomb branch. So this very schematic argument about deforming the profile of masses shows that, oh yeah, and I introduced here some complete set of boundary conditions. Such that basically at the level of Q cohomology, you can say that some normalization so this schematic pictorial argument with the deformation of masses and phi parameters shows that indeed the reason that the vertex function or this vortex partition function of the Higgs and Coulomb branches are related in such a non-trivial way is realized by this Janus interface or phase transition interface in this physical setup. And well, I guess I've run out of time. I just will say in words that this thing also admits interesting observables where you can either insert surface operators wrapping the cigar and the circle, or line operators sitting at the origin of at the tip of the cigar and wrapping the circle And one can, in fact, show that deforming one into another is a Q-exact deformation again. So it's a slightly unusual setup when the line and surface operators are equivalent to each other in the Q cohomology, because you can shrink it like this. And the line operators, their algebra, the line operators you can insert at the tip, and in particular, they include Wilson lines, whose algebra gives the realization of quantum K theory. But then this argument shows that the same is also realized via such surface operators here in the bulk. And it plays a role in the Bethe-gauge correspondence, where there is actually a much larger algebra acting by surface operators. And this type of lines, which I didn't really describe but mentioned here, they sit in the Cartan subalgebra of that larger algebra. But anyways, I think I will stop here.